Do we need to go over how to convert from moles to grams, grams to moles, moles to particles, particles? Do we need to go over that? All right. So if we know conversion factor, that's all it is, right? Just like converting from feet to inches, it's the same thing. Good? All right, so if we have 1 mole of anything, how many particles do we have? 6.022 times 10 to the positive 23. It's a whole bunch of them, right? Particles. And those particles, so this is a review if you want to. Particles, what are the different types of particles? What are the particles of an element called? What's the smallest particle of an element? Atoms. What's the smallest particle of a covalent compound?
Particles?
Elements.
They are particles. But what do we call them?
Molecules.
Molecules. Molecular compound is the same as a covalent compound. Okay? Molecules. And what do we call particles that represent an ionic compound?
Ions.
Almost. Formula unit. Well, wasn't really almost, but okay. Have you ever heard that before? If you call it molecules, it's not going to hurt my feelings. Because most people do. Particles of a compound, okay, molecules, right? But they're not called atoms because they have multiple elements in it, right? And if we have an ion, which is a charged atom, we just call it an ion. That's a particle, right? So these are the 4 different types of particles that we could have, depending on what compound we have or what substance we have. Are we good? Okay. So here is our conversion factor. What element, what compounds or what element does this work for? All of them. So we can say we have 1 mole of carbon. How many, what are the particles of carbon called?
Molecules?
Good guess. Try again.
Atoms.
Why are they called atoms?
Because
Because carbon is an element. It's not a compound. It's not a, right? So this is 6.022 times 10 to the 23 carbon atoms. Are we good there? So this is just a conversion factor, and we can do it for all the elements on the periodic table. 1 mole of any element is 6.022 times 10 to 23 atoms of that element. That's a conversion factor if we want to go from moles to particles or particles to moles. Are we okay with that? Do we need to go over an example of converting this? Okay, let's do it. So you guys have these worksheets. The top 2 are from last time, and the bottom 2 are for today. Okay, moles to particle conversion. Top of this worksheet. Okay, let's just do the first one. How many moles of magnesium is 3.01 times 10 to the 22 atoms of magnesium? So we're looking for number of moles. So whenever we do a conversion, dimensional analysis, we start, what's the question? What are we looking for with the units, right? How many moles of magnesium? That's what we're looking for. And this is what we have. So where do we start? With what we have, right? We have 3.01 times 10 to the 22 atoms of magnesium. And write it all out. Don't get sloppy and lazy, but just write it out. And we're just converting this. Do we want atoms of magnesium in our answer? No, what do we want? Moles. So atoms of magnesium on bottom, so they cancel. And we're looking for moles of magnesium. Well, what's the conversion factor from moles to atoms or atoms to moles? One atom? 1 mole, because that's the bigger one, right? How many atoms? 6.022 times 10 to the 23 atoms. That goes away. We're left with moles. That's what we're looking for. So that's it. We just take this number and divide this number. Do we understand why we divide? Are we good with this? Okay. So I gave you, how many conversion factors did I just barely give you? Thousands of them, right? 1 mole of anything is the same as 6.022 times 10 to the 23 particles of that thing. What if we have 1 mole of, I don't know, Tommies? What if we have 1 mole of Tommy? How many Tommies do we have? Anybody know?
What are Tommies?
Tommy's right there. If we had 1 mole of Tommy, how many Tommies do we have?
6.0.
A lot of Tommies, right? Oh, I'm sorry. 6.022 times 10 to the 23 Tommies. Doesn't matter what it is. 1 mole of whatever. 6.022 times 10 to the 23 particles of that, whatever. Good? And we can start with moles and go to atoms. Moles and go to molecules, or whatever. Any questions on moles to particles, particles to moles? Okay? Do we need another example, or are we okay? All right, moving on. If we have magnesium oxide, what is the molar mass of magnesium oxide? Do we remember how to do this? Yeah, add the atomic masses for each one. So magnesium, look at your periodic table. Was 12? Not quite. That might be the atomic number. We need to know the atomic mass, which is what? Point.
3.1.
So 24.31. Oxygen is 50.99, basically 16, right? And we add those and we get 40.31. What are the units? What? No? Good guess. Not quite. So those numbers at the bottom on your periodic table, the atomic mass, that's grams per mole. That is another conversion factor. 1 mole of magnesium has a mass of 40.31 grams of magnesium. That's the conversion factor. One over the other, flip it, and you can use it as a conversion factor. So how many conversion factors did I just give you? Thousands of them, right? Does that make sense to everybody? Should we do a problem? So all we did was just figured out the molar mass. Do we understand how to calculate the molar mass? Yeah? All right, so let's do a problem here. How many moles are there in 28 grams of carbon dioxide? Okay, we know what we're looking for, and we know what we know. So let's start with what we know. We have 28 grams of carbon dioxide. What goes on bottom, everybody?
More grams.
Grams of carbon dioxide, so they cancel, right? Not grams of oxygen, not grams of carbon, not grams of water, but grams of carbon dioxide. That's why it's important to write what substance you have there. Don't just get lazy and write 28 grams. Because then later on, we're going to be dealing with a lot of different substances. You might get mixed up on which one we're dealing with, okay? So just write everything out. So we know grams to what?
Moles.
Grams to moles, molar mass. Do we know what it is for carbon or carbon dioxide?
44.
Okay. You got 44, let's check it. What's the molar mass of carbon?
12.
Basically 12. Oxygen is 16 times 2, that's 32. Add those together, yes, we get 44 grams per mole. So where does the 44 go, on top or bottom? Where?
Bottom.
On bottom, 44 grams per 1 mole. That's it. So grams goes away, grams of carbon dioxide go away, and we're left with moles of carbon dioxide. That's what we're looking for. Tells us we can stop with conversion factors. Now we do 28 what?
Times
28
times 6.022.
We could do that. Is that what that tells us? I would do what we're doing. And this is why it's so important to show your work so you know what to do. Do we need to use the 6.022 times 10 to the 23 in this one? No, because we don't need to know how many particles. We don't know how many particles, so we're not going to use that one. We know grams, and we need to know moles. So we need grams per mole. That's this one right here. Right there. So what do we do? 28 in our calculator. What do we do?
Times 44.
Times 44? Divide 4? How do we know? Do we multiply 44 or do we divide 44? How do you know, Veer? Oh, it's on the bottom. Oh, yeah. Is there a 1 underneath that? And if you guys like to do it this way, you can. Some of you have mentioned that you just like to do it the way you learned it, which is a long time ago in 6th grade or something, right? 28 multiply 1 is 28. 1 multiply 44 is 44. Now you have fraction. What does that fraction bar mean? Divide, right? 28 divide 44.
0.6.
And you can do that all day long. It'll always work. But I'm just going to show you the way I'm thinking. You don't have to do it the way I do it. You can do it that way, the way you learned in 6th grade, or whatever. 28, that's on the numerator. You always start with what you're given. Divided by, there's a multiply right there, but it's multiplying by 1, right? Multiply the guys on the numerator. Divide the guys on the denominators. Does it matter the order you do it if you have multiple conversion factors? No, it doesn't. Okay, and we talked about this first unit, right? Okay. Are we good with this? So what's 28 divided 44?
0.63.
0.63, what are our units?
Moles.
Right here. These canceled out, and we're left with that one right there. So not just moles, but moles of carbon dioxide. Good? And the last one we did was moles to liters, moles to volume. And we only learned it for what kind of substances? Not liquids,
Solutions?
not solutions. Well, could be a solution. gases. It only works for gases. Because remember, if you have a temperature that stays the same, temperature of 0 degrees Celsius, and a pressure that stays the same at 1 atmospheric pressure, then the volume will be 22.4 liters per 1 mole of any gas at that temperature and pressure. But if you change the temperature or the pressure, that number will change. But it'll change the same for every gas, because all gases behave the same way. Are we good? So there's our conversion factors for gas at STP. Standard temperature, standard pressure. We good? Questions? You want to do an example? Yeah? Okay, let's do it. I don't know if I gave you practice for that one. Whoops, I thought I did. Let's give you another one. Okay, let's say we have 30 grams of oxygen gas at STP. And we want to know what's the volume of oxygen. We know what we're looking for? And maybe it says volume in liters. We start with what we know. This is what we're given. 30 grams of oxygen gas. What goes on bottom? Grams of oxygen. Right? What can we convert to? Can we convert straight to liters yet? Do we know how many grams there are in a liter? Well, we know how many grams there are in a what? In 1 mole. 1 mole of oxygen gas has how many grams? 32. Oh, right here. 16 times 2 is 32 grams per mole, right? So 30 divided 32, well, should we just keep going because we're not there yet? Yeah, let's just keep going. We're not there yet. What goes on bottom? What? Well, we do divide by 32, but we're not done yet. What goes right here? Moles, right? So moles go away. Do we want moles in our answer? No, let's get rid of them. But we know moles to what? Liters of oxygen. Here's our conversion factor right here. 1 mole to every 22.4 liters, but that's only at STP. Okay? That goes away, and we're left with liters of O2. And that's what we're looking for. 30 divide 32 multiply 22.4. Don't have to worry about the ones. And what do we get? 21, let's see. Well, if we start with 30 grams, that's 1, so we should probably just say 20, right? For rounding to the right number of significant figures. 20 what?
Liters per mole.
Liters of O2. Nope, moles canceled out. And this is why it's important to show your units so you know what you have and you know what you don't have. All we have left is liters of O2. That's it. Does that make sense? So I have a lot of students that try to just do this in their head. They just try to get a calculator and just go to town on it. You're going to mess up. Maybe not always. you're going to mess up if you do it that way. And if you want to get an A in this class, you don't want to mess up, right? Some of you are doing real good at that, but getting an A. All right. So that's conversions. The molar conversions. And we're going to use those for the rest of the semester, which month left, a little less than a month. Okay. Ready to move on for today's stuff, or do we have any questions? All right. We also talked last time about solutions. Do we understand solutions? Did we study that at all? If we don't study what we learn, we're going to forget it. And then we say, dang it. Right? Are we good with solutions? Okay, who can tell me this? What does that mean? NaCl parentheses AQ. It doesn't mean water.
It's a water solution.
Okay, it's a water solution of salt, sodium chloride, right? Where this is the solute, and what's the solvent?
Water.
And water. So this right here tells us it's water, aqueous. That is the not solution, but solvent, the dissolver stuff. Good? All right, now I have a whole practice there for determining which one's the solute and solvent if you want it. Okay? Any questions on that? We good? Ready to move on? All right. 22 minutes and we're just getting into the lesson. Sorry. But here we go. You guys asked for it. All right, concentration. You guys ever heard of concentration before? What ever heard about it? What is it? What? What did you hear? Oh, concentration, like you're concentrating. Wrong one. Yeah, so there's two meanings, right? Darn English. Okay. So concentration for solutions means what?
Like saturation, like the amount of a solute in the solvent.
Yeah, how much solute there is in the solution. If there's a lot of solute, then we say it's highly concentrated, right? If there's not very much solute, it's a low concentration. Are we good? So I'm going to give you, rather than a definition, I'm going to give you an equation, a formula. Oh, I got to memorize formulas. If you remember this formula, then you can understand all of the other ones. Okay? Got a few formulas this lesson. So concentration. In fact, when I think of concentration, every time it goes back to my childhood. You guys use concentration in your childhood? Besides that concentration game with cards? Orange juice, right? You guys ever have orange juice concentrate? Can of frozen orange juice concentrate, and then you dump it in a pitcher and you pour water in it to, what are you doing when you pour water into it?
What's the word?
Yeah,
Make it less concentrated.
Yeah, what is that word? We dilute it, right? We dilute it with water or solvent, and it becomes more or less concentrated. Less concentrated when we dilute it, right? But you guys ever go to the freezer and sneak a spoonful of this stuff?
Sugar.
Yummy. Okay, whatever. And if you don't have that experience, I'm sorry. Okay, so concentration is equal to amount of solute divided by amount of solution, not solvent, but solution. And this is always what it is. Amount of solute over amount of solution. What do I mean by always? Is there another equation we can have?
Solute over solvent?
Well, what does amount mean?
Like a quantity.
It could be grams, right? It could be grams. What else could it be? Liters. What else could it be? Use words that we just learned.
Moles.
Moles. It could be moles, right? It could be all that stuff. So the amount, whatever it is, the amount of solvent or solute divided by amount of solution, okay? Now, the main unit of concentration that we use in chemistry is called molarity. And it's still amount of solute over amount of solution. Didn't change. But what does molarity kind of sound like? What does it have in it? Moles. So it's moles of solute over, now this doesn't really sound like it, but it kind of does, larity, liters of solution. So the symbol that we use for molarity is capital M. Don't get that confused with mega, right? Molarity is moles per liter. Those are the SI units for molarity. Good? But what else is this besides a formula? It's a conversion factor. We know how many moles there are per liter. Good? Or if we have a volume, we can convert it to moles. If we have a number of moles, we can convert it to liters. Make sense? All right, let's do an example. Any questions so far?
Would that be like the same as like just saying like mass over volume?
Would it be the same as mass over volume? Moles over liter. Is that equal to mass over volume? What do you think? This is density, right? And this is concentration. Are they the same? No. Good question. Good? All right, let's do an example. Okay, if we have 1.25 moles of glucose in 5.40 liters of solution, we want to know the concentration. So determine concentration in molarity. Do we have to know a formula here, guys? Do we have to know memorize those equations? Do we have to memorize the density equation? Do we? When we did the density problem on the midterm, did we have to memorize that formula? We didn't. If we did, it may have made us get it wrong, right? Because the units didn't work out. But if you use dimensional analysis, you'll get it right without the formula. We got to know one thing. What do you got to know? Concentration is solute over solution. Always. If you know that, you don't have to memorize formulas. Good? So get that down. So let's do this. Where's our solute?
1.25.
How do you know this is our solute, Vir?
It's the smaller quantity.
What?
It's the.
Because it's moles?
'Cause it's,
What's another reason?
'cause
It says
it's
the smaller quantity.
Oh, because this is solution, right? That's the solute, so we just got to recognize this is our solute, and this is our solution, right? So concentration is 1.25 moles of glucose, solute, over solution, which is 5.40 liters of solution. What else do you have to know? You do have to know something. You have to know, if we want it in molarity, we have to know what molarity is. What's molarity measured in? Somebody, anybody, one buddy. Moles over liters, right? That's what unit we're looking for. So I like to write molarity as moles per liter rather than just M, because that doesn't tell us a lot, right? But moles per liter tells us everything. Okay, so that's what we're looking for. Do we have that? Moles per liter. Yeah, we're done pretty much. We don't have to really convert anything. But did we even have to know that formula? Could we have? Yeah, we could have. Okay, yeah, either way. 1.25 divided by 5.40. We should get 0.231, 3 sig figs, 3 sig figs. So we should have 3 sig figs. We can call it moles per liter, or we can call it 0.231 molarity of what? Glucose. So either one. Does that make sense to everybody? Should we do another one? Let's do another one. Unless you have any questions on this one. Good? All right, if we have 0.825 grams of ethanol, which is C2H6O. So this is the stuff they put in our gas, right? In 700 milliliters of ethanol solution. We want to know what the concentration in molarity is. If you feel like you got this stuff, do it on your own right now. If you need help, I'll do it right now. Who needs help? Y'all want to try it? Good. Anybody need help? I can do it right now. But if you can't do it on your own, you won't for the test either. And I know we just barely started this, but practice this. Ready to try this? Okay, here we go. If you guys want to keep going on your own, that's fine. All right, so this is a concentration. Which one is we got to know solute and we got to know solution. So Eduardo, what's our solute in this problem?
the
The ethanol. How do we know this is our solute?
Because the solution is.
Oh, because this is our solution, right? Yeah, easy enough, right? And whenever we have a solution, let's say we have a solution of salt. Which one is the solute? Salt. If it was a solution of alcohol, alcohol would be the solute. Or did I say solution is salt?
Yeah.
Sorry. Which is the solute? Salt is the solute, right? If I have an alcohol solution, alcohol is the solute. If I have a Kool-Aid solution, what's the solute? Kool-Aid. We call it by the solute. And what's the solvent in most of these? What's the universal solvent? Water. Is it always going to be water? No, but most of the time it will be, right? So that's how we can tell. So here we know this is the solute. So how do you find concentration?
You divide
Divide what? What on top?
by the solute.
Solute on top, 0.825 grams of C2H6O. And what goes on bottom?
700 milliliters.
Solution, 700 milliliters of solution. All right. Is that all we need to do? Just divide them? Why not? How do you know?
Because we want grams.
Oh, we want molarity. And molarity, we need to know it is measured in what?
Mole.
Moles over liter. That's what we have to know. Are we good? And if we know that, we have a formula, right? But gosh, we don't have moles, but we know how to convert that to moles, right? We don't have liters, but do we know how to convert milliliters to liters?
Yep.
I hope so. It's a long time ago, right? So then we just convert. What do you want to convert first? Grams to moles or milliliters to liters? Doesn't matter. Okay, yeah, it doesn't matter. Where does grams go, top or bottom? On bottom, so they cancel out. Grams of ethanol. What goes on top?
1 mole.
Moles. 1 mole of ethanol has a mass of what?
46.
Is it 46? Did anybody else get 46? Okay, we'll go with it. 46 grams. But that's just the molar mass, right? Whoops. So that goes away. And now we have moles per milliliter. Are we there yet? No. So we got to keep going. What goes on bottom? Do we want moles to go away?
Yeah.
No, we better not cancel moles then. No, that's really what you got to do. Ask yourself, what do we want to cancel? What do we want to cancel? What unit do we want to cancel? Milliliters. So where does milliliters go? On the top. So that they can cross cancel, right? So we know milliliters to what? What can we convert it to?
1 liter.
Liters, right? Liters are bigger, so 1 liter. How many milliliters the same as 1 liter? 1,000. Hope we know that one by now. That one's the most common one we use. Milli, right? Okay, so no, liters don't go away. Milliliters goes away. Now we have moles per liter. That's what we're looking for. That tells us we can stop. Everything else canceled out. Do we understand dimensional analysis? This is what we use in chemistry. If you don't like it, well, sorry, we're in chemistry. Get good at this, because if you're good at dimensional analysis, chemistry is not too bad. Now, when you get into higher chemistry, it gets a little bit more difficult, but this is the basis of chemistry. Okay? But in this class, that's it. Okay, we're not going to go hard math in here. Conversions, that's basic algebra, that's it. All right, so we have the right units. What do we got to do in our calculator? 0.825, then what? Always start with the top left, because that's how we read, right?
Multiply by 1000.
What do we do?
Multiply by 1000.
Multiply by 1,000. Is that okay to multiply by 1,000 first? Yeah, doesn't matter. So you can either start all the way to the left and go to the right, or you can start at the top and then do the bottom. It doesn't matter. Multiply and divide, same thing in order of operation, right? Same. So let's go ahead. We got 0.825 multiplied by 1,000. That's all the guys on top. Then we can just divide what?
700.
Divide 700 and divide 46 before you ever push equal. One calculation, equal once. And what do we get? Something. 0.0256. And let's see. 3 sig figs. 1 sig fig. Oh, we better go with 1 sig fig. 0.03. And we can call it molarity of ethanol or moles per liter of ethanol. Either way. Good? Easy enough, or do we have questions? Because if you can't do this on your own, we better have a question. Because you got to get to where you can do this on your own. And remember on the midterm, there's a density problem, kilograms per centimeter cubed, right? But we wanted grams per centimeter cubed, so we had to convert it. Make sure you know what units you need, okay? Who wants another example? I have one right here. But if we feel good about it, we can move on. But if we want another, and I have one right here, you tell me. One more? Perfect. Thanks for telling me. I don't want to waste your time, but I don't want to go too fast and make sure you don't understand it. Okay, so next one. We have 4.75 grams of calcium nitrate. Anybody know what calcium nitrate is? What? I'm talking about as far as what you learned in this class. What is calcium nitrate? What kind of compound is it? Ionic compound because it has a metal in it, right? Has ions in it. Okay, it's an ionic compound. And what's another name we call ionic compounds? You remember? Salts. This is just a salt. This is not the salt we eat, but it's salt. Okay? What happens when you throw salt in water? It dissolves, right? Okay, it dissolves and forms a solution. That's it. That's all we're doing here. Okay? In a solution, so this is in 0.200 liters of solution. What is the molarity? Go ahead and do this, and I'll give you the answer. And if we want to still go through it together as a class, we can. But if we all get the right answer, then I guess we're good. So there's the answer. See if you can get it. Don't try to fudge numbers until you get it. It's not a good way to do it. So if you can't get it first try, then let's go over it. And that's the answer if I did everything correct. I could have given to you, who knows.
0.1448.
Rounds to how many sig figs? 3 sig figs. Good? Got it? Who wants to go through it? Anybody? Doesn't mean you're stupid, it just means we want to go through it. Make sure we got it. We're here for you. If you don't got it, let's go through it. Yeah, you want to go through it?
Yeah, I started with the doing the solute divided by the solution.
Which one's the solute?
The 4.75 grams.
Good. 4.75 grams. And there's another way to do this. Do you guys want to know another way? Is this confusing to anybody? If it's not, keep it up. Let me show you another way. We know molarity is what? Moles over liter. That's what we have to know, right? Do we have moles here? No. Can we just convert this to moles?
Yes.
And we've done this last time and this time, right? So what's the molar mass of calcium nitrate?
154.
154?
164.
164. Okay. We good with that? So we got 164 grams per 1 mole. And that'll give us how many moles we have, right? And what do we get? 4.75 divided 164. 0.029 moles of calcium nitrate, right? And then we come over here. We say, all right, is this what we're looking for? Do we need liters of solution?
Yes.
Yeah, we got liters, so let's just divide that by 0.200 liters of solution. And now we have moles per liter. That's another way to do it. If this confuses you to put it all in one big chunk problem, don't do it that way. Good? But if you like doing it that way, it just makes it one problem instead of two, do it. Whatever you like. Just make sure you end up with moles per liter, and we should get that there. 3 sig figs. Questions? We good? All right. Let's do a slightly different type. Let's say we have 0.250 liters of a 0.15 molar solution of potassium bromide. We want to know how many grams of potassium bromide are there.
Just to multiply both.
Do we multiply them or do we divide them?
Multiply both of them.
I don't know. Yeah.
Wait, no.
Multiply.
Multiply? Should we just vote on it? No! Write it out! Write it out. A lot of you guys want to do this in your head. What happens when you do stuff in your head half the time or most of the time or some of the time? You mess up. Because you can't see what's going on in your head. Well, that's how my head works. If I can't see it, I make mistakes. So let's just write it out. We know what we're looking for, and we know what we know. Where should we start? We have two knowns. Which one should we start with? Should we start with 0.250 liters, or should we start with 0.15 molar? Molarity. Molarity, yeah, I'll start with molarity. Sure, why not? Or if you want to start with 0.25 liters, go ahead. Doesn't matter. 0.15, what should I write instead of capital M?
Moles over liters.
Moles over liter, yeah. That tells us way more information. Let's use that. So we have 0.15 moles of KBr per how many liters? 1 liter. Molarity is moles per liter. If we're going down the highway at 55 miles per hour, we go 55 miles in how many hours? 1 hour. Per 1 hour. Do we have to say per one? No, it always is one, right? So it's per liter, per 1 liter of solution. Okay? And, well, what do we not, do we want moles in our answer? Do we want liters in our answer? No, we want grams in our answer. So we got to get rid of both of these. Which one should we get rid of first? Moles or liters? Doesn't matter. Your call.
Moles.
Moles. Okay, let's get rid of moles. Where does moles go?
Bottom.
On the bottom. Got moles on top, moles on bottom. They're going to cross cancel, right? That's it. Moles of KBr. And we know how to go. What do we want to go to? Oh, we want to go to grams, don't we? Do we know how to go from moles to grams? We should know, right? What's the molar mass of potassium bromide? Potassium is, what is it, 40? I don't remember.
39.10.
So 39, and bromine is set 80?
79.9,
It's about 80. We add those together and we get 119. So 119 grams of potassium bromide for how many moles?
yeah.
1 mole. Grams per mole, right? Okay. So here moles go away. Now we have grams per liter. So what do we got to get rid of, or are we done? Get rid of the liters. Where do liters go? Top or bottom? On top. Cross cancel, right? So we have 0.250 liters of our solution. Do we need anything on bottom? What goes on bottom? 1. Why not? Or just leave it blank, right? We don't have to write a 1, but that's what it means, right? Liters of solution goes away, and we're left with, we are left with grams of KBr. That's what we're looking for. That's it. 0.15 multiply 119 multiply 0.25, and we should get 4.46 grams of KBr. Is that the only way to do that problem? No. But, I don't know. How do you feel? Good? So in this case, this was basically just what? Or sorry, this right here was basically just what? a conversion factor. Well, not that one. This is a conversion factor. This right here is just a conversion factor. If you didn't want to say, what do I put on the bottom? I get a lot of students to say that. What do I put on the bottom? Well, if you don't know what to put on the bottom, just start with that. Do you have to put anything on the bottom when you start with it? No. But do you have to put anything on the bottom if you end with it? No, you don't. Either way, it's the same. Good? Questions on molarity? All right. Let's move on to dilutions. We talked about making orange juice, right? We dilute it down so we don't have to eat the whole can of concentration, right? So what does it mean to dilute something?
Make it less concentrated.
Less concentrated, right? Or how do we do it? How do we dilute something? By adding what? Adding solvent, yeah. In the case of orange juice, what's the solvent? Water, right? That's it. Okay, so let's these are the exact same containers. Pretend. They don't look like it, but they are, okay? And let's say we throw some water in there and we put some food coloring in it. And it's pretty red. Good? Now if we add water to it and fill it up to here, hold on. It's gonna look like that, right? Well, it doesn't look the same on my screen. Let's change that a little bit. That look any better? No. Let's try it again. That any better? Does that still look a little red? Okay, not quite. It looks like it on my screen. Whatever.
Cross it with the red.
It's just a lot less red, right? It's more whitish. Are we good? More clear? You understand what I'm doing though? I accidentally deleted that. Okay, so we go from a lot of red to a little bit of red. Good? By just adding water. Okay, how many moles of red food coloring do we have here versus here? The same, right? We didn't change the number of moles of solute. We just added water. You with me? So N, we represent the number of moles. V stands for what? Volume, liters of solution, usually. And M stands for Molarity. Or moles per liter, right? So our formula is what? Molarity equals N over V. Are you with me? Okay. So if the number of moles here versus here, they are the same, right? Can we solve this equation for the number of moles? How do we do that? Multiply volume to both sides, right? And we got the number of moles equals molarity times volume. You with me? Is everybody okay? Talk to me.
Looks
Good? Okay. So if we say N1 is equal to the molarity of our concentration 1 times the volume of concentration 1, and N2 is equal to our molarity of concentration 2 times our volume of our concentration 2, right? Does that make sense to everybody? And these are equal, then we can say M1 V1 is equal to M2 V2. Write that in your reference sheet, and you don't have to memorize it. But if you understand how I got it, then you can, whatever. All this is molar, or this one's molarity, right? Use a little algebra, and we get this. This is our dilution equation.
The
M1 V1 equals M2 V2. Can we also say equals M3 V3 equals M4 V4? Yeah, whatever, right? If we dilute it, this only works for when we dilute something, when we add the solvent, right? All right. Let's use a problem that uses this equation. Let's say we have, now, if we have, let's say we need to do an experiment. We need to do a reaction, and we need, it calls for 0.5 molar solution of hydrochloric acid. And then the next day, we need to do another one. We need to say, okay, we need it more concentrated. So we need, let's say, 1 molar solution of hydrochloric acid. And the next day, it's like, okay, that wasn't enough. We need to make a higher concentration. Let's make it 2 molar, and then 5 molar, and then 10 molar. Do we go to the store and buy a solution that's 0.5 molar concentration? And then 1 molar concentration, and then 2, then 5, then 10. No, we buy 1 concentration of hydrochloric acid. Should we buy a high concentration solution or a low concentration solution?
high,
Why high?
because
Then we can just do what?
dilution.
Dilute it. Add water, right? And that's how it works. I go to the supply room, the chemistry supply room, and I have, let's say, a 12 molar concentration of hydrochloric acid. You get a drop of this in your eyes, and you're probably gonna really, I don't know if you'll go blind, but it's gonna hurt, okay? You might go blind. Don't try it, okay? And let's say this is what we have, but we want to make, let's say the concentration, we need to make a 0.5 molar concentration of HCl. How much? let's say we need 200 milliliters of a 0.5 molar concentration. But this is what we have in the stock room. How do we make it? Any ideas?
You figure out how much you would need for the total of the solution
Of which one?
of the 200 milliliters.
And
So,
We need 200 milliliters
yeah, so you
of
figure out
this.
how much of that would be made up of hydrochloric acid and then you add water, or however much.
Yeah, we add water to this, but how much of this do we need, right?
Right.
Is that what we're looking for? We need to know the volume of this, right? Okay, which concentration is our first concentration? Which one is our second? Does it matter? No, it doesn't. Which one should we say is our first? The one we start with, right? Should we just say this is M1 and this is V1? And we could have done it the other way, right? No big deal. If we say this is M1 and this is V1, then what's this? V2 and this is M2. This is our second and this is our first. We could also have said the first one is our second one and the second one is our first one. Doesn't matter. Is everybody okay? Am I saying too many words? Okay, here we go. So we know the equation, dilution equation is M1V1 equals M2V2. What are we looking for? V1. Can I solve for V1 before I put any numbers in?
Yeah, just
Divide M1 to both sides. And we got V1 equals M2V2 over M1. Is everybody okay with that mathematically? And it's a lot easier to do this without numbers than with numbers, right? Sorry, I didn't say that right. It's a lot easier to do this without numbers, right? Yeah, I said it right. Okay. All right, so what's M1, M2? 0.5 molar. And what's my V2? 0.2. Do we have to change this to liters? Let's try it without and see what happens. 200 milliliters of my solution, right? Because if we don't have to convert, let's not. But maybe we do. Let's see. Divided by, what's M1? 12 molar, right? And when it says molarity, I just call it molar. I don't know if you guys recognize that. 12 molar solution, okay? All right, what cancels? Molarity, right? Molar goes away. And I'm left with milliliters. Is that okay? Unless the problem says how many liters of 12 molar solution do I need, right? But it doesn't. It just says, how do you make this? So what's 0.5 times 200 divide 12? I didn't do this beforehand, so somebody give me the answer. 8.3 repeating what? But what are the units? Yeah, milliliters. That's all we have left, right? Milliliters of 12 molar solution of HCl. So we measure out in our bottle 8.3 milliliters. Did we make this yet? No, we need 200 of it. We only have 8.3. So then what do I do? What do we do?
You subtract 8.3 from 200, and the remaining will be what the.
That's how much water we put in,
Yeah.
right? We just dilute it. We just put the rest of water. So we do 200 subtract 8.3, and we get what? 100.
91.7.
91.7 milliliters of water. All right, does that make sense to everybody? So that's how we would make a less concentrated solution. Good? All right, let's do another one. Let's say we add 25 milliliters of water to 125 milliliters of 0.15 molar concentration of sodium hydroxide. We want to know the new concentration in molarity. So what do we do? Yeah, we determine which one is which one is solution 1, which one is solution 2, right? Okay. M1 equals 25? What do you think?
It's the volume.
Oh, that's a volume, right? So what's M1? X, we don't know?
Yeah.
Or can we just call this M1? Because that's what we start with, right? We have that, and then we add something else to it, right? We could have done that too, Beer. That's okay. Either way, doesn't matter which one is solution 1, which one is solution 2. Doesn't matter. But let's just start with what we know, right? We have 0.15 molar solution of sodium hydroxide. What's V1? If M1 is 0.15 molar, what's V1? 125. That has to be, right? If we choose that, if we choose our M1 to be 0.15. So our M2, we don't know. That's what we're looking for, right? So we could have said that was M1 also. No problem. And V2 is what? Is V2 125? Or is V2 25? Yes or no?
Yes.
I want you to think. Do we end with 25 milliliters? What do we end with? 150 milliliters. Does everybody understand how we got that? We just added 25 milliliters to 125 milliliters. We diluted it, right? We got 150. Now we want to know the new concentration. So do you see where this gets a little tricky? You got to think about what's going on. You can't just, oh yeah, I'm just going to plug the numbers in and just get it, right? You've got to think. Good? And now that we have everything labeled out, we can use this equation. And what are we solving for? M2. Let's divide both sides by V2. And we got our equation M2 equals M1 V1 over V2. And then plug the numbers in. If you like to plug numbers in before you solve, do it. That's okay. Just because I don't like to doesn't mean you don't have to do it my way, right? Do it whatever makes sense to you. Who likes to plug the numbers in first? Okay, let's do it that way. Let's try it. But I want you to try it both ways. Because when I started doing this, I was the same way. I like to plug the numbers in first. Until I did it the other way, I was like, oh, this is way better. But that's me, guys. That's me. You don't have to, but try it both ways, okay? So let's try it first with plugging the numbers in afterwards, right? So we got it set up, solved without numbers. So M1 is 0.15 molar. V1 is 125 milliliters. And do we have to convert? No, because they're both milliliters, right? Divided by V2 is 150 milliliters. What cancels? Milliliters goes away. And we're left with molarity. Good, that's what we're looking for. We're looking for the concentration. 0.15 multiply 125, divide 150. So M2 is equal to 0.125 molar. Is that what you got? What?
You need to put the answer into sig figs.
Oh, yeah, let's see. Sig figs, we have 2 sig figs here and 2 sig figs here. So 2 sig figs is what it should be, right? 0.13 molar solution of NaOH. Good. Good? Do you want to try it with plugging the numbers in first? Let's do it. So we have M1 V1 equals M2 V2, right? Our M1 is 0.15 molar, 0.15 molar solution. Our V2 is, V1 is 125 milliliters. And our M2, we don't know, we'll just write M2. And our V2 is 150 milliliters, right? Are we good? We got to solve for that. So what do? Divide by 150 milliliters. Did we get the exact same thing? Yeah, same. Doesn't matter which way you do it. So just because I like to do it one way doesn't mean you have to, okay? Do it the way that feels more comfortable for you. We're going to get the same answer. Good? Are we good with dilutions? Write that dilution equation on your reference sheet that you get for the final. And you don't have to memorize it. But practice using it. I gave you a worksheet over here that you can practice. And I'll put the answers on the modules. Good? Okay, let's move on unless you have any questions. Do we need to take a quick break? Or do you want to move through? Break? Okay, let's take a little break. If you want to practice doing this on your break, go for it. If you want to use a restroom, get a drink, whatever. Go ahead. Did you say 5 minutes? All right, any questions on concentration and molarity and dilutions? All right, there are a few other concentration units that we're going to go over. But what do you got to know here? It's solute over solution, always, right? Always the same. All right, so let's deal with mass percent. Can anybody tell me how to calculate mass percent solution? This is a concentration. So it's mass of what?
Element.
Solute. solute, right? Mass of solute over
Massive solid.
mass of solution. But we're dealing with percentage, so what do we got to do?
Divide by 100.
Times by 100. Right? If you have a fraction, change a fraction to a decimal by dividing, right? How do you change the decimal to a percentage? Multiply by 100. That's it. Does that make sense to everybody? Okay. But what do we have to know? These better be in the same unit. So if the solute's measured in grams, the solution better be measured in grams. If it's in kilograms, better be kilograms. Micrograms, micrograms. Good? Okay. So let's do an example. If we have 355 grams of solution, and we have 36.5 grams of sodium chloride. What is the mass percent? Mass of solute on top. They're both in grams, so we're good, right? 36.5 grams of sodium chloride over mass of solute or solution, which is 355 grams of solution. Is that all we need to do?
And then you multiply by 100.
Multiply by 100 to change it to a percentage. That's it. What cancels?
The grams.
Grams goes away. So what do we get? 10.28% what?
Solution. Or solute. Mass percentage.
Well, what? It's 10.28% what? Of what? What are we dealing with here? Sodium chloride. Our solution is 10.28% salt. Good? Does that make sense or no? Because when we have a solution of alcohol, what are we interested in? Alcohol. When we have a solution of salt, what are we interested in? Salt. You guys ever look at the, let's say we're dealing with isopropyl alcohol, rubbing alcohol. You ever look on the bottle of the rubbing alcohol? What does it say? 70% alcohol, right? That could be percent mass, or it could be percent volume. If we go buy vinegar in the store, it's 25% acetic acid. It could be volume, it could be mass. It's probably volume. Okay? But that's how we do it. That's percent mass. Mass of solute over mass of solution times 100%. Are we okay with that? What about volume percent? Percent by volume. How do we do this? What's the equation? What's the formula? Somebody give me a guess. Volume of solute over volume of solution. Is that it? Times 100, that's it. Not too bad, right? Same. What do we have to note here? These guys better be in the same unit. They better be both milliliters or both liters. Why? So they can cancel. We're looking for percent, right? Our unit is percent of whatever our solute is, right? Does that make sense to everybody? I'm losing half my class here. No, not half. Okay. Student example? Okay. So let's say we have 500 milliliters of a 70% solution. Well, of isopropyl alcohol, C3H8O. This is rubbing alcohol. We want to know how much alcohol do we have? Volume of C3H8O equals what? What is it?
350 milliliters.
Okay, well, I don't know. He probably did the math right. Well, let's work it out. How do we do this? Here's the formula. Plug the stuff in, right? What's this? That's that. 70%, that's the percent volume. Do you get that? That's not mass, that's not volume, that's percent. So 70% is equal to, so 500 milliliters of this so we have 500 milliliters of that stuff. What is that stuff? That's the solution, right? This is what we buy in the store. And we have 500 milliliters of this. That's a solution, right? 500 milliliters. We want to know what's the volume of alcohol. And this is our solute, right? Or is it? What is it? %70 alcohol. So what is alcohol? That's the majority of it. So what's alcohol here? That's the solvent. What's the solute? Water, right? If we want to know do we want to know how much water we have? We don't. So what are we going to use here? If this is 70%, what are we going to put on top here? Water or alcohol? Alcohol, because that's what we're interested in, right? Did I confuse anybody? Okay, so this is going to be volume of isopropyl alcohol, C3H8O. Because that's what the question asked, right? Who cares about solvent and solute right here? Times 500 to both sides, right? Is it just 500 times 70? It is, but we forgot something in our formula. What did we forget? Times 100. We better divide by 100% too if we do that. Right? That goes away. That goes away. Oh, and this is just 0.7, right? So yeah, we can multiply. We just have to make sure we don't forget that 100%. Are we good? Did I confuse anybody? Let's do another one. So that one wasn't, I mean, in any problem, you have to know what you know and know what you're looking for. So why didn't I just give you a simple one? Give you the volume of solute and volume of solution, and then find the percent volume, right? You could. I could give you that. And I might give you that on the homework, and I might give you that on the quiz or the test. But I also might give you one that you have to solve for something else. You have to solve for volume of solute or volume of solution. Good? So, should you write this equation down? Write it down. Have it on your reference sheet. And then if you get, oh, you forgot, it's been a while, you can still use it, right? Plug the stuff in. Make sure you know which one is the solute, which one is the solvent, and what you're looking for. Good? All right. We're going to do some more of these, but let's do, what if we have percent by mass volume? So when we did percent by mass, it was mass over mass, right? We did percent by volume, it's volume over volume. But if we do mass or percent by mass per volume, when we did this over here, what canceled? Grams canceled. If we do volume over volume, they have to be the same units, so milliliters cancel or liters cancel. And we just get percent. How's this going to work? Mass of solute over volume of solution, and it's percent, so we got to times by 100%. How's this going to work? Do units cancel? They don't. So this only works if we have a solution of water. If water is the solvent. Good? And here's why. How's mass related to volume, guys? Do we remember? Density, right? Well, the density of water is 1 gram per milliliter, or 1,000 1 kilogram per liter. Good? That means 1 gram of water is equal to 1 milliliter of water. Do these cancel out? They do, if it's a water solution. And so we can only do mass per volume, and sometimes we do, mass per volume percent if it's an aqueous solution. Are we good? So this only works for aqueous solutions. Good? So let's say we have questions on this. Did I lose anybody? Okay. So if we have 45 grams of sodium chloride in 1,200 milliliters of solution, what's the percent mass volume percent? So what do we have to look for? Mass has to be measured in grams, and the solution has to be measured in milliliters. It has to. Or kilograms and liters, right? But if we have kilograms of this and milliliters of that, we got to convert. It's got to be grams per. In fact, if you just know it's grams per milliliter, just get rid of that, because it's mostly grams anyway, right? And mostly milliliters, sometimes liters, but has to be grams and milliliters. Good? And it has to be what? An aqueous solution, water solution. Good? So here we have, this is a, and what happens if it doesn't tell you what the solvent is? Like this one doesn't. It just says we have 45 grams of sodium chloride in 1,200 milliliters of solution. It doesn't tell us what kind we have. Then what? If it doesn't tell us the solvent, then it is water. Because water is the universal solvent. Good? So we have 45 grams of sodium chloride in 1,200 milliliters of solution. So we have grams per milliliter times 100%. These are going to cancel since it's a water solution. And we get 3.75% sodium chloride. Good? So I know I give you a lot of formulas today, and I'm going to give you a couple more. But what do you notice the same in all of them? Solute over solution. And then if it's a percent solution, then it's times by 100. That's just regular percentages, right? Just like when you find the percent you get on the test, you take what you got, divide by what you could have got, divide the total, times 100, always times 100, always. Are we good? All right. And we're going to do other percent problems here, but percent problems are the same no matter what you're dealing with. Percentage is always the same. Who needs help with percentages? If you do, please let me know, okay? All right, let's move on to the last type of concentration. And we use this type of concentration if we're dealing with small amounts. This is a very low concentrated solution, okay? So if we call this parts per million, and parts per billion. What's a part? Not quite. A part could be a gram. A part could be an ounce. A part could be a cup. You guys ever go on, what's it called? What's that? Pinterest? And you might get a recipe on how to do something, right? Maybe they want you to, okay, you want this beautiful color of paint, but you can't get this paint at the store, so you have to put red and blue and you ever do this? And what does it say? 5 parts of this to 3 parts of that to 1 part of that. You guys ever do this? Okay. Well, what does part mean? Whatever you want it to mean. It can be a gallon. If you want to make a lot, make it a gallon. If you want to make a little bit, make it an ounce, right? So part could be anything. And what do we use here in chemistry? Milliliters, moles, grams, particles, whatever, right? So we can use anything we want, but it's got to be the same part. We can't do 5 gallons of blue with 2 cups of red. It's not going to be the same parts, right? Does that make sense? Okay. So, wonder what the equation is for parts per million. It's still a concentration. So this could be grams, if we're dealing with grams, or milliliters, or even liters or kilograms or micrograms or whatever, right? Whatever we use. But if we use grams of what? What goes on top? This is a concentration. Grams of solute. Over what goes on bottom? If we use grams, what goes on bottom? Grams of solution. But we want to make this parts per million. We times by 1,000,000. How does that work? Let's see. Let's say we have, and this is for like in our water. What else is in our tap water at home? Fluoride, chloride, right? And the FDA says you can have so much chloride or so much fluoride and it's still not bad for your health, right? And I don't know if they're right or wrong, but okay, that's what they say. Has to be fit in with the FDA standards, right? So their FDA standards might be 200 parts per million, ppm. Good? So let's see. How, if we have 7 grams of solute, let's make it easy. 2 grams, let's make it even easier. Let's say instead of 200 parts per million, we have 2 parts per million. If we have 2 grams of solute, how many grams of solution must we have? 1,000,000 parts per million parts. 2 parts of solute per 1,000,000 parts of solution. Does that make sense?
Skip the miles per hour, like the
Yeah.
the slash.
Parts per million. In this case, it's million, not just one, right? Parts per million. So that's 1,000,000 grams of solution. And then we got it times by, not 10 million, by 1,000,000, right? Well, what cancels? 1,000,000 goes away. Does 2 equal 2? Do you see how that works? Okay, what's the equation for parts per billion? We could use milliliters this time. Guys, just know that you can use milliliters on both, and you can use grams on both. You can use moles on both. You could use ounces on both, right? Doesn't matter. Milliliters of solute. In fact, I should just say amount of solute, right? But they have to be the same unit. And could it be grams and milliliters? In the case of water, right? Just like we did mass per volume percent. Okay? Milliliters of solute over milliliters of solution times what? 1 billion. That's it. Are we okay? Oh, we're out of time, aren't we? Sorry. We'll go over those examples next time. How's that? Sorry. But that's it. That's the whole lesson, except for examples. And you will get examples on critical chemistry, so don't forget to do that. Anyway, any questions? We need an example. We'll get there next time, okay? Sorry for going over.